All right, we are back for part 2 of section 2.1 lecture, Elements and Structure of the Atom. So we left off here looking at the properties of the atoms and a visual representation of protons and neutrons in a dense nucleus where all of the mass essentially is contained, surrounded by electron cloud that makes up the rest of the atom. So the mass is almost entirely comprised of protons and neutrons. The volume is essentially determined by the electrons, and the charge would be determined by the relative number of protons and electrons. I always like to point out that, of course, protons and neutrons are not blue and red, and the electron cloud is not green. Um, Strangely, this same color combination I find on lots of different pictures of atoms. And of course, there's no color really to these parts. Okay. Now, the size of these things. Let's take a quick look at the size according to your textbook. On page, I believe it's 45 and 46, it says that a carbon atom has a diameter of 140 picometers. And then on page 46, it says that the nucleus has a diameter of approximately 1 times 10 to the minus 15 meters. Okay, I thought that we used units to make numbers comparable, right? And with these two numbers, we cannot compare them. Okay, we know that a nucleus is small relative to an atom, but do you have a good concept of what a picometer is or how small or what all this means? Probably not. So what I want you to do is write the diameters of the nucleus and of the atom in the same unit. So you choose what unit you want to use. And then determine how much larger the larger one is than the other, right? So you can pause this and do this by yourself, and then when you come back, we'll do it together. Okay, so we already have the nucleus given in the base unit of meters. So we should probably just convert this to meters and then we can compare. Okay, so the atom is 140 picometers, and 1 picometer is 1 times 10 to the minus 12 meters. So I can say 10 to the minus 12 meters over 1 picometer, and I get 1.4 times 10 to the minus 10 meters. So now if I take the question 2, atom size over nucleus equals 1.4 times 10 to the minus 10 meters over 1 times 10 to the minus 15 meters. And we get that the atom is 140,000 times bigger than the nucleus. Okay, so that is a very, very small nucleus relative to the size of the atom. And the picture that I've put here may have kind of given that away, right? That imagine a football at the center field. The football to the whole stadium is like the nucleus to an atom. Okay, so when we say that it's very small and dense, it's very small and dense because even the atom itself is small. But it's 140,000 times bigger than the nucleus. Okay, let's move on to the next subsection, which is elements in the periodic table. So an element is actually defined by the number of protons in its atoms, and this number is known as the atomic number. If we look at a periodic table, we see that every element has a different atomic number. 1, 2, 3, 4, 5, 6, and so on, right? And they just count right up, never skipping a single one, all the way up. So we see that the periodic table, there's lots of ways that it's arranged that we'll talk about, but one is it just goes in order by number of protons. So the difference between a hydrogen atom and a helium atom is a proton. Add one more proton, and now you get lithium. Add one more proton, and now you get beryllium. So the element is defined by the number of protons in its atoms. Each element with different numbers of protons is assigned an atomic symbol, which would be the letters. So it's either one capital letter, or if it's two letters, it's always capital and lowercase. When we get to writing chemical formulas, talking about molecules, chemical reactions, we'll use these atomic symbols a lot. Another thing that we see here is the atomic mass. Okay, that's the average mass of atoms of that element. So the way that this table is arranged is quite brilliant. Okay, we clearly see like from left to right and top to bottom, the atomic number is increasing, but there are also lots of other ways in pieces of information, relationships that are expressed in the way it's put together. An interesting point about this table is that it was written this way before all of the elements were actually discovered, and there were holes left in it. Right? Once we got the pattern, we noticed that there was a spot, between atomic numbers, and predicted what would be found and what properties it would have based on its position in the periodic table, and it was correct. Now, the rows here are called periods. So we have period 1, 2, 3, 4, and so on. And the columns are called groups, and they have A designations, 1A, 2A, 3A, 4A, and so on. And so we'll make some sense of these and how they relate to electronic structure in the future. But for now, we can talk about periods being rows across the table. Groups are columns down the table. And there will be certain properties that are common within groups and common within periods. Okay, so to summarize, the periodic table, each cell here shows us atomic symbol in the middle, telling us what the element is, atomic number, which tells us the number of protons, and atomic mass, which is the average mass of the atoms of an element. How about a question about that? Without going back, what is atomic number? You can pause it, and it is equal to the number of protons in each atom of an element. All right. Let's review the subatomic particles. This is practice exercise 2-1. Fill in the blanks. Blank and blank are located in the nucleus of the atom. Blank has a negligible mass. Blank has a positive charge, and blank has a negative charge. Your possible answers, remember, are proton, neutron, or electron. And we get protons and neutrons in the nucleus. They make up all of the mass, essentially, and electrons have negligible mass. Protons have positive charge, and electrons have a negative charge. Okay, another string of questions here, and here's another one. Calcium, it's atomic number 20. Let's go back. Right here. Okay, I found that quick because, well, I know where calcium is, but you can find that quickly because I just told you that it's atomic number 20. And so you see they go in order. So we find, 19, 20, there it is. And atomic number 20, it's a major constituent of bones and teeth. So how many protons and electrons are present in a neutral atom of calcium? What do you think? Pause if you want to. All right, so the answer is 20 and 20. How did we get that? Well, remember, atomic number 20 means protons. Atomic number is number of protons. Protons is atomic number. They're the same thing. So if it's calcium, we automatically know there are 20 protons. Now, it says, how do we know how many electrons there are? The key is that it's neutral, a neutral atom, which means the number of protons and number of electrons must be equal because the plus charges and the minus charges cancel out. All right, here's another one. How many electrons are present in a neutral atom of potassium? The tricky part here is probably finding potassium on the periodic table because you need to know the atomic symbol. And this is one that's not based on English, right? It has nothing to do with our name for it. The atomic symbol for potassium is K. Yes, K. If you were paying attention when we looked at calcium, potassium is right next to it. Right there, K. Okay. So there's atomic number 19. So if it's a neutral atom and it has 19 protons, because atomic number 19, then it must also have 19 electrons. All right, we will end part 2 here and come back for part 3.